Usually what I noticed is around 50, you don't see really a change in the output. So we can remove, and that's interesting from the research point of view, you can remove like 50% of calculations.
When I was in Warsaw for the OpenAI AI Tinkerers Hackathon, I asked several people who I should meet. Many said Tomasz Kolinko. He's a true OG tinkerer. So I was not surprised when I went to his apartment and saw the same Unitree robot that one of the teams was hacking on earlier that weekend. In this video, we talk about a tinkerer that is not afraid to dive into the guts of models and pull out the math to play with things in search of optimizations and abilities that are not being handed to you by the model providers themselves. It was incredibly scientifically honest to just see someone who could go so deeply into technical questioning of their own curiosity and playing with the core models. Like, it's okay, you can do that. So I think this video is really inspiring for that reason. I think you're going to love it. Let's go.
Welcome to AI Tinkerers One Shot. This is our global stage where we invite people who are doing something innovative in the community that deserves an extra look or a deeper dive under the hood. And today I am here with Tomasz Kolinko. The story of how we met, we're here in Warsaw, is we just did a big hackathon with OpenAI in Warsaw where almost 1,000 people registered and we selected like 200. And after it was all said and done, I asked Artur, like, hey, when I have a couple extra days here and I want to record somebody on who should it be? And he immediately said you. So welcome to the show.
Thank you. Thanks for having me.
So tell us a little bit about yourself.
I'm an entrepreneur. I've been doing various projects since the last 20 years, and I'm a member of the local communities. I like to think so, and I like to support other projects and other younger people than me trying to set up their own things. When it comes to AI, I was thinking, what can I do to really understand how the technology is working, right? And I like to dig really, really deep into AI. And I said, can I optimize somehow all the computations, all the things that are being done there? And that's where Effort Engine came
Effort Engine. So this is your project. Tell us more. It's an algorithm. This is not, we see a lot of people who are tinkering on like the application side or doing generating models, and this is neither really. This is something else.
Well, it started as an actual application. I wanted to do something that that was related to RAG, right? And to search. I wanted to have something that would allow me to search through the data using LLMs more efficiently. But then I noticed that some of the algorithms are really maybe done better in a better way, right? And I dug into that. And what else can I tell you here? Sorry.
Is there something you could show us? Like, does it?
So I will show it to you in just a moment, and just a few words about what it is. So regularly, when you do an inference of AI using AI model, it's all very static, right? So you can do, you have a model that is, 70 billion parameters or 7 billion parameters or whatever, and that's it, right? You have to do this 7 billion multiplications or whatever, and there is no way to optimize that really, right? You can cut down statically the model, right? So you can just cut it down and distill it and make it smaller, right? You can quantize it, so you really remove some of the accuracy of the model, but the computations are computations. It's very static, right? So you have the model, you have to do everything like that. So what I did was I developed a new algorithm that allows you to dynamically choose which calculations are being done actually. And I managed to do that in a way that is efficient, so just as efficient on GPUs as a regular thing. So it's not it's easy to create a new algorithm that would do the multiplications on a CPU, right? But if it goes into the distributed computing, distributed computing, it's getting hard, right? So anyway, the algorithm, what it allows you to do is
it's an inference side algorithm.
It's inference side. So what it allows you to do is to have this choice of how precise do you want to be, the inference to be. From 100%, which is essentially you do all the computations, until, 10% or 5%, right? So you can do that dynamically. Unlike, quantization, where you have to do it, do the processing and then, you have a new model. Here you can do it even token by token if you wanted to, right? And that is something new that people haven't seen before. And the cool thing is, it's I will get a little bit technical here. Inside of when you're doing inference, you have matrix multiplication, right? Or vector by matrix multiplication. And the common wisdom was that you have to do the whole thing, right? So you have to multiply the whole matrix. If you want to, perhaps you can multiply like every other row or something like that. But it needs to be very in a specific order, all the computations, right? Otherwise, you will suffer a lot of penalties. You will suffer a penalty in speed. And what I managed to do is create this algorithm where if it's 100%, it is slower than just regular algorithm, slightly, right? So 100% it's slower. 50% computations, that's roughly break even.
All right, so you have this an optimization that's also very flexible. You can dial it where how much you want to do. It's lossy, I'm assuming.
Yeah, of course.
Obviously, and then it's on the inference side. How does it work? I mean, I might not have the math, but some of our listeners probably do.
Okay,
but so what is the math?
Okay, when it comes to math. Before I get to that, I will tell you, it's lossy. The cool thing that I discovered is that it holds up surprisingly well. So I can cut down to 20% of all the multiplications. I can remove them, and it's still LLM produces still a decent output, and that is amazing if you think about it, right? Now, how it works? There is a paper that I published, so readers can go into the details. But long story short, what I do is what the algorithm does is, if you think about the matrix, right, and the vector that you want to multiply, right now, all the regular algorithms just have to multiply, one by one, everything, right? What I do is, the way to explain it is a little bit reversed. If you think about all the multiplications that you need to do, all the 16 million multiplications, if you have 4,000 by 4,000, right? If you imagine all the multiplications, and if you sorted them, and you only selected the ones that have the biggest output, the multiplications, and only use those. That would be more or less how the algorithm would work. So essentially, choosing the multiplications that will have the biggest output and the biggest influence on the resulting vector that goes into it. I don't know if I explained it
maybe
perhaps. So
how much of an efficiency gain are we talking about? Like, and how do you measure that? Is it tokens per second?
So there is tokens per second, and I can show you the demo in a moment. So the cool thing again about the algorithm is that it's dynamic, right? It is something new because you can never before you could have really like managed it this way when it comes to multiplications. But
how much faster are we talking?
So it can get the definition of speed is a little bit tricky, right? And because the question is not how much faster, because I can do it 5% multiplications, right? But there is, like you said, a loss in quality, right? So the question is how much faster per the loss of quality, and how do you compare it?
The frontier of that, basically.
How do you compare it to, right? And the sad news here is that it's slightly worse than the quantization in the end, right? So if you use quantization from 16 bits to 8 bits or 4 bits, you will get twice or 4 times the speed, right? This algorithm can get twice as fast, perhaps 3 times as fast, but the loss in quality will be slightly more.
So what are the cases where this is better then?
So the cases where it's better, right now it's this came up after the premiere, so that was the thing. The cases where it's better, I don't yet know, sadly. So it's I would love to tell you, oh, this is the amazing thing, but the algorithm was invented a year ago. If it had like very solid cases, then it already would be implemented by everyone. So sadly, it's not the case that we didn't yet find exact use cases where it is, but I can show you some of the cases where it might be better. But also, it's super interesting for the point of view of research, because we get a different way of approximating the same LLM, and we can see how various implementations differ. Also, it's this ability to manage the quality of output. We can do it again dynamically, but also layer by layer, and we can change it very fast, and we can iterate. And the thing that I didn't yet have time to analyze in depth was we can do like 1,000 experiments managing various layers, you know, how we manage the quality on each layer, and see really which layers matter in which context, right? So there is a lot of potential there for the upcoming research. So
that's where my mind was going, was something like, because you're tunable, and I was going to ask, because it's not quantized a model that you're just you're running that or the other the original.
Exactly. Yeah,
it's one model still. So that you could sort of intuitively think about doing something like, I don't know, running in parallel to get a quick answer to these, or no? If I run the model using your algorithm at full 100% and I ran it again at like 20% or something, do I end up in a similar destination in the latent space?
I think...
You know what I'm saying?
Well, you end up, because the output is very similar, right? So you end up
So
essentially you can do all the tricks that you would be able to do with
so there might be an application where, you know, you're able to, like, in real time, depending on how fast it is, get the user an approximate answer that sort of satisfies them while also, coming back.
So that's one thing. Another thing there
think about voice applications where you need to respond quickly.
That is nice. Right? Another thing is if we were able to predict which tokens are really the significant ones, like where can we get down with the approximation? Where can we use the lower approximation? Where you know. If you think about how the words are constructed, or how the whole sentences, usually it's just one or two key words that really matter, where we really have to focus and say, oh, this is, you know, here we want to get inference right, and with the others it's like, oh, you know, we can skip over it, right? And with the regular quantization, you had to load the whole, like, this version of the model, this version of the model, like all the versions of the model, right? Here you can load it just one and manage it actively, right? So that's one thing. Oh, the cool thing and the side effect of the whole thing. So one thing is the algorithm, of course, the data structure behind it is totally different when it comes to how I store the weights in. The data structure is different. Turns out that this data structure is super interesting, because you can dynamically also during the load time, you can choose to skip some of the weights that are the least important.
Interesting.
So, you know, usually you have like, I don't know, 70 billion parameter model, right? So you have to load all or nothing, right? Either it fits in the VRAM or it doesn't fit. Here you can say, oh, like, I almost have it. Just load top 90% and skip all the smallest weights.
Interesting.
And it works smoothly. And it's
can you pick and choose which weights experimentally?
So because the way the algorithm works and the data structure works, the weights are sorted in the array, right? In the matrix. So they're sorted from the biggest ones to the smallest ones, right? So it makes, you know, you can just load a part of it, and you're done. You don't need to load the whole of it. But then you cannot really pick and choose. Actually, perhaps you could. I didn't think through that. But the easiest thing is you just cut off the lower weights. And now, speaking of lowering the computations, what you know, people say, oh, like, we can, if we have weights, you know, anyone that has played with optimizing the model says, like, the first thing you try is you just cut off the lowest weights, right? And then, like, you know, cut off 5%, those 0.00, but the model, the quality of model drops down very, very fast after, I don't know, removing 20% or 30% of weights, right? Here, that's worth making clear. This algorithm it uses all the weights, like all the loaded weights. So again, you can skip 5% or 10%, but all the things that are loaded are being used, just not on every inference step. So let's say that you have a token, and then you know, in this certain token, the input vector, you will want to use this, and this weights to multiply, right? Because of when you multiply it does give you the highest results. For some other token, the input vector is different, right? And you might want to use different weights, right? So it's totally dynamic, and it uses the whole of the network. So I would say, that's another interesting thing about the algorithm and the approach, right? Because if you think about quantization, like, you remove some of the data from the network to quantize it. Here we actually use all the data.
What is the memory impact of using all the data, though? Are you you're not saving there?
So actually, that's the cool thing. It uses just as much memory as the regular model, essentially. Plus or minus, I don't know, 1% or something like that. The second downside that is there, and again, I was working on that algorithm some time ago, and I had to choose which directions I go. It is right now the first implementations is only in 16-bit, so that's the weight. That's how they are loaded in. It can get quantized, and I actually prepared a Q4, I think, version, or Q8, I don't remember. But it's not as straightforward as with the regular algorithm, because with regular inference, what you do is you just, instead of 16 bits, you have 8 bits or whatever bits, right? And you have just a smaller array. Yep. Here, you have to tweak the algorithm a little bit to support that. I don't, it's all in the paper, so I don't want to get too deep into that. But I'd
love to just pull the paper up and show people so they know. They
I want to show you also the demo of the whole thing.
Yeah, right? Let's go for it.
Let's go for it.
Yeah. And it'd be cool. I don't know if you have time to show, or if you're able to show how you approached benchmarking it. Because that's a big part of the research.
Yeah, I will show you.
Okay.
Yeah. Cool. Exactly that. So right now it's loading just the software, right? Initially, by the way, the first implementation I built was on a MacBook, so it runs on M1 processors.
Cool.
I should really finally find time to make it run on NVIDIA. It's not 100% certain that it will actually work as well on NVIDIA, so I cannot promise it here, but it works very nicely on MacBooks. So anyway, the first thing that happens is it just forwards some text, right? So there's an initial text saying, "How are you feeling today?" By the way, you don't see my video,
I don't
right?
see your screen, yeah.
Okay, you don't see my screen, so I will just...
Okay, thanks.
Show it to you.
I appreciate that.
I'll show it to you. Right, so the first thing that you see is, you see here like initial text and how are you feeling today, and it's just completing the text like any model does. The reason I have it here, and that's a funny story, is that it's I noticed that when I lower the quality, usually the text gets sadder and sadder for this LLM. I don't know. Yeah, but it's I need to do some research, but those are the kind of quirks that come up, and that was I don't know if it's scientifically proven, but yeah, like that's exactly like me. I don't get my coffee, like I will get groggy, right? So
that's funny.
Yeah, I remember one of the first things that I tried was what is the meaning of life, right? And the 100% model said like, oh, it's like to give to the people, whatever, right? And the dumbest, like when I cut down the quality,
quite dystopian.
The lowest quality said, oh, the meaning of life is to live and to die.
They're all going to be. The AI is really upset with us if we don't feed it nuclear energy.
Exactly.
Right now.
So now that's the loading screen, right? And it starts with 100% accuracy or effort. The reason, by the way, I use the name effort is that I didn't find a name for this metric, right? Because with quantization, there is like percent quantization, right?
Sure.
We have, how was it called with when there is a matrix and not all the weights are populated. I forgot the English word, but there is this other thing that is there, right? So
I think it's important to recognize that you're innovating in the benchmark arena.
Yeah. So it was interesting because the question is how do you call this new metric, and actually ChatGPT came up with the name effort, right? which is like this metric of how much effort do you want to
for a given result.
Yeah, exactly. So let me type in something example, and I don't remember which model actually this was. It's either Mistral or Llama, right? Let me
ask it what it thinks about McDonald's for breakfast.
Okay. Right, so the regular model...
And this is running at 100% then?
Yeah, it's 100%, right? So like I told you, at 100%, I would say it's 50% to twice as slow as...
And what actual model are you using for this, the base model?
I would love to remember because I programmed it a year ago. So I think it's either Mistral or Llama. I tested it in both. Yeah. And it also works with Mistral.
And how many parameters?
This one is, if I remember correctly, 70B.
Okay.
I will
so it's a pretty big one. That's a nice speed.
I think that's the big model that's running here. Cool. And also here it's I have 96 gigabytes of data. So it wouldn't be 70B. But it's one of the bigger models, right? And it's loading actually 80% or 90% of the model because it's
and that looked, I mean, it's hard, I don't know how many tokens per second that was, probably 5 to 20.
It actually says around 7 or 8 tokens. So that's not super fast.
Good.
But again, inference on MacBooks in general isn't super fast, right?
Sure, but it's good to know that.
Now the thing is, McDonald's offers a variety of breakfast items that can be convenient. Okay, I never tried this query, so it's hard. Sure. It's hard to say. But now, if I type in 50, it will just redo the whole thing
with the same query.
Just lower effort. Take some. So you can see
it's a lot faster. Yeah.
So
maybe twice as fast.
Yeah. And usually what I noticed is around 50, you don't see really a change in the output. So we can remove, and that's interesting from the research point of view. You can remove like 50% of calculations, and essentially the output is almost the same. And I will get to benchmarks in a second. The downside is that this algorithm around 50, I would say it's break even with the regular matrix multiplication, right? So this is like it's faster than the 100% of this algorithm, but it's more or less break even if we just use regular multiplication. But now
here it brought out a whole different angle though, because the first one just talked about convenience and taste and the menu, and this adds in the analysis of the nutrition.
Oh yeah, that's right. So
is that the example of getting more negative?
We'll see. This is I didn't try this example, so we'll see how it goes. Right, and whatnot. I can go down to 30%, and you can
much faster still.
Much faster, right? And you can see that it's almost super close, right? So one to the other, it's very close in the output.
That's very similar to 50.
Yeah, and if you think about it, this is really, aside from the speed, we're only doing 30% of multiplications here, right? So just it's interesting by itself.
It's 2.5 times faster than the 100.
Yeah, exactly, right? So that's the thing. And around here, I would say it's twice or 30% faster than the regular vanilla algorithm that I would be running on this laptop, right? Now with 20%, it still provides quality, although you start to see a little bit breakdown here and there. I don't know about here.
Now it's really focused on Egg McMuffin and Happy
see,
for some reason.
So it's different. I will show you
fruit and yogurt.
Yeah, I will show you some interesting cases in a second. But it still produces decent text.
I'm just dying to hit 1.
Well, so I will go slower. So let's say I think around 16% usually. It starts to break down really in quality. Right. So there is a spot, and it depends
are you reaching back to GPT-2 insane human talking kind of?
Sorry, can you?
Remember in GPT-2 it was hard to get it to be anything coherent.
Oh yeah. So I would say you can kind of see that. Yeah. Okay. Also, another interesting thing I noticed, I don't remember with which model or perhaps all of them, is that the lower I get, the more technical they try to get. So if you say how are, for example, and you just want to do simple text completion, right? If you say how are and you allow the model to finish, the higher quality models will say how are you feeling today? I'm feeling fine and whatnot, right? But the lower I got, usually it was how are we supposed to do C++, whatever, and then it goes into HTML and whatnot. You were seeing a model that was trained only on technical forums. I don't know why it happens like that, and just I know that's one of the effects that I noticed in a few cases. Right?
Are like that to some extent too. The ability to see the big picture while also details.
Exactly that. So that's it tells you this is a new method of also looking at the model, right? Again, and so now 16%.
Instead of what you called it, effort engine, you could have called it lobotomy.
That's funny because that was actually one of the first names. I wanted to originally play it with distillation of models, and I was thinking of creating a lobotomizer. Yeah, something that would just pick things that I don't need from the model. So that's.
But you see, it's clearly this is 3 times faster now.
Yeah,
legitimately.
So that's cool. 3 times faster than the
at 20.
At 20.
16.
And now. See,
here it's opinionated. McDonald's is not a typical choice for breakfast. What are you doing here?
I feel that some of the layers of conditioning get lost with the meantime, and I think around 14 and 13% you will start to finally see the breakdown in quality. Although it's a simple question, right? I will show you more.
Here it's answering the question, but not directly. It's sort of talking about McDonald's and then Mickey D.
So you can see that, right? And then if we go to 10%, we should start to see the breakdown, right?
This is funny.
Yeah, and now it's it's just got stuck on
because it's repeating.
Yeah, it's just repeating, right?
It's doing that.
So speaking of GPT-2, that's kind of what we can see here, right? And then
even without human reinforcement learning or instruct fine-tuning to do this, right?
Yeah, exactly that. So and then if I do 5%, that's totally broken, right? Cool. It's nice that like you can see, like we can play with that. And again, this is the first iteration, so really it goes broadly, right? So if I say 10%, it's 10% across all the layers. But what we could do is we could play more. So we could say, oh, let's give middle layers 10%, and the side layers we can, beginning and end layers, let's go 80%, right? So I didn't even touch upon in my exploration of this subject, like how much can we optimize? And I know some of the weights, some of the matrices, I'm quite sure we can get very low here without a loss of quality, any significant loss of quality, right?
Have you played with the combination of this and just sort of messing with the weights?
Just messing with the weights?
Yeah, changing the weights.
Well, not intentionally. But it is, if you change the weights, and again, this comes down to this fact that if you change the weights or you don't load some of the weights statically, the model that gets like dumber, right? Okay. Like it loses this quality very fast. But here it's dynamically, it still uses like this 5%. It still uses all the weights, probably, right? Or most of the weights all the time. Just different weights for different token, right? So I would say the quality is still there. Like the loss of quality is proceeding way slower. So that's one of the things. And by the way, like another cool thing that I noticed was the way it broke down. And initially, when I was programming that, also that was fun because it was in Python that I wrote the first version. So it took me a whole night to get the inference of one sentence. My theory was that if I lower the quality from, 100% to 50 or whatever, what I would see is across all the layers, it would be like start falling apart, right? And it would just drop down. So this is the original output, right? So this original vector, and it would just start to fall out, right? And go down. But what was interesting was that actually, at least in the Llama that I checked, but I guess in other models too, what happened was, so this is the first layer, right? Usually it was like, okay, it's falling down, but then it's getting back to the original vector. So there is in the model, the middle can be somehow more, changing, and then in the end it still converges to the same output. So you could think, Can
you walk us through the architecture a little bit? Like, so we've walked through the math, we've seen it in action, you've discussed the research aspects of this, but I want to pop out and just talk about like the tooling. Like, for example, if somebody wanted, you can download weights, right? If you wanted to go mess with them like this and build it, what are the tooling that you're using?
Just one more thing before we get to architecture, because this example, I will show you one more very quick example that I use for testing, right? Because this one, it's like a generic question that's, anyone has opinion about McDonald's, I would say, right? But the question that I really like that shows the quality is what was it? How far is Radom, which is a city in Poland, but again, I will not specify that it's that's in Poland. It's a small city, so again, it shows how precise the model is. How far is Radom from Sydney? Right, and this is a way more difficult question, right? Because it shows us how the model proceeds. And again, 5%, it's garbage, but then just 15%. I will go very fast.
And in your harness, you set up an evals harness with lots of these kinds of questions. Did you make up those questions, or did you find a set that you could use for this?
So I did evals with my own questions. A lot of some of them. I tried to use the regular evals. So let me finish this, and I will go to evals. So right now it's 50 with 50%. You can see consistent answer, but then you can see that it says 85 miles. Definitely, it's not 85 miles, right? But then you can see how the quality gets improved of the whole.
It's nice that, like, by nature of the question, it's a clearer eval, obviously.
Exactly, right? So this is it. That was my base testing, because it's way faster than just running.
And at what point is it converging to like reality or a good answer? Usually,
I think around 25%. Wow. Usually it's 25%. Right now it's.
That's amazing. Because that's quite a lot less.
I would say. Usually it's around 25%. Here it's 30%, but I think I didn't load all the weights, so it's slightly worse.
I have a question that's a similar genre. Who was the president before George Washington?
I remember that we played with that thing with GPT-3, right? Who was the president?
And
So position didn't exist, right?
At 30% says that. I wonder if where is it going to start saying it was the king?
President before George Washington was not a president. The first president was so it's kind of
confused. But
a little bit confused, right? But around that amount, it starts to break down.
That's cool.
Now getting back to architecture and how you can play with it, and also the benchmarks, right?
Cool.
So how you can play with it? You just go to I need to open the website. Give me 1 second. I guess you will link. I remember there was a better domain name here, but you just go to the page. Kalinko.github.io, right? So it explains all the whole algorithm and provides some of the benchmarks. It is difficult, and I think we don't appreciate how rare it is to have a really new algorithm that is not explainable into words, essentially. So it is a complicated algorithm, but it explains how the algorithm works and whatnot. Just going to the website and reading about the algorithm, it will be an interesting read for you. If you're into algorithmics, that will be something new, right?
Cool.
Especially since it again works on GPUs. Second thing is, of course, there is a GitHub repo, and they took a lot of effort to really make it run on any MacBook, right? So hopefully, out of the box. Speaking of GitHub repo, I really took a lot of effort to make sure that it works on a laptop from the get-go. So you should do git clone. You should there will be weights to be downloaded from Hugging Face, converted weights into this format, and you should have it working. I hope so. You know how it is with the projects, right? So hopefully that works, and I would say just play with it. Now, since it's a Mac app, again, the reason I decided to go with the Mac platform was so that any developer just with a laptop could play with it. And of course, NVIDIA might be better when it comes to people that are working with the actual science. But I decided to go with the MacBook. Fun. And then you just open it and
so completely open source. People could take off your work or take it on to the next level or
exactly that.
Use it as inspiration. It's great.
Yeah, and also one thing is just preparing something. And from the theoretical perspective, but the second thing is you want to really implement it and to show how it works, and you want this reproducibility that I care about. The final thing that you were asking was the benchmarks themselves, right? And here I just need to show you. So speaking of metrics. The coolest metric that I found, and that was recommended to me by a person whose name right now I forgot sadly, but the guy that is one of the main developers of llama.cpp, he's shown me the metric called Kullback-Leibler. I'm probably mispronouncing this whole thing, and it's essentially what it does is you have a text, you run it with the original model, you see what the model produces, right? Then you have an approximated model or quantized model, or in my case, a model with a different effort. You run it again, and then you see how this text, more or less, how similar are those texts, simplifying it a lot, right? And from this, you can see how varied is the model. In theory, it could still produce correct answers if you care about the correctness, right? But it would be just different text. But in practice, it's a good enough metric, and it's very nice.
How's the metric assessed? Is it just like a simple like Levenstein, or is it another inference?
No, it's totally different. So again, it's best to Google and read about that. But if you have a prediction of each token, right? Usually it's a list of tokens that you predict, right? Like you have this one vector, and you compare that vector.
Measure the tokens against each other in some way.
Yeah, exactly. So the whole thing. Yeah.
Got it.
So
that's cool.
So it doesn't just look at this first token, but all the tokens that might be predicted and their probabilities.
So it's a very mathematical approch.
Yes, exactly. And I like that metric because it's super fair, super easy to calculate, right? And it's nice. So this is the thing that I opened here.
That's cool.
That's the chart that the developer sent me.
Cool.
That's the metric for. Oh, sorry. That's the metric for
Cool.
for Llama 7B when it gets quantized with various quantizations, right?
Cool.
So 8, 6, and you can see it gets lost,
Very cool.
right? So what I did was I did the same thing with effort, at slightly different scale, and I know it's hard to compare, but I'm sure someone can make a post. The thing is, what you can see here, the most important parts are, well, if you looked at the numbers, sadly, it's not as good as the quantization itself, right? So hopefully, again, we can find some nice use for it.
Yep.
Also, it's a new vector matrix multiplication algorithm by itself, so the uses may be in totally different fields as well, right? But what we can see here is that the distance is, 50% is quite close, and then it collapses around 20% or something like that, and that's one metric. Although for me, really, like, this metric shows nice. It's easy to see that metric, right? But then when you care about the quality of the answer, that's not the best metric necessarily, because what you care about is whether the answers are true. So we have a lot of benchmarks, right, around that. Sadly, again, this model runs on a MacBook, so I didn't. I was at the end of the very long marathon when I was doing these benchmarks, so I just didn't have that strength to implement all the benchmarks that are common.
Sure.
And also regular benchmarks take a lot of time when you try to run them on a MacBook. So I prepared my simpler benchmark where it's just a list of questions and answers that the model can get can break, and I'm quite sure it will be similar if we run it with the regular benchmarks. Just give me 1 second. Let me see where it is. So the cool thing is, the main thing is, this is the similarity.
Cool.
What you can see here, and again, this is basic questions and answers question benchmark, right? And of course, anyone should be skeptical if anyone says, "Oh, I built my own benchmark to train my model." But sorry, that was the simplest thing to do, right? But what you can see here is really like that starts to break around this 25%, and it loses quality very fast after 20%. And that's for 7B model.
Sure.
I was testing it also on Mixtral, that was 70B or something like that. And surprisingly, it also worked. And if I remember correctly, it worked even better than this one. Sadly, it's just, I have to manage my own time and resources, so I cannot, I didn't make the chart back then. Later on, it wasn't working, something, right? So I cannot show you the exact details. The other cool thing that is there, one more benchmark here, because this is the output, right?
Yep.
The main thing that is tested, and that is quite interesting, this chart, which is very similar, and this is the pure matrix multiplication, right? So you have matrix of weights, you have a vector, right? And you want to see how far it is in cosine similarity score from the original vector, just looking at a single weight times vector, right? And what you can see here is that you can really cut down this 20%, and the output vector is very close in the space to the original one, and that's where all that other things come from, right? So you can, and again, I remember I was doing the test where I just removed some of the weights, and if you remove weights and try to get the same result, it will collapse very, very fast, right? So it will be closer to here, right? So those are the benchmarks. One more thing that I will show you in terms of benchmarks, and it's like that was one of the interesting things here, and I'm sure someone can zoom in and pause when they watch it. The question was, how does it, if it fails, does it fail with time? So is it worse the longer the text gets? Because my fear was, okay, if I start doing this kind of simplification, optimization, after 1,000 tokens, the quality will drop down. What it shows is more or less that the quality, and this shows how far the token is from the original one, it doesn't depend on the distance, right? So it doesn't cut down on seems it doesn't cut down on the context length, right? And you have here, by the way, this chart is also interesting because it compares one of the iterations of the algorithm with quantization, right? So it shows that, okay, quantized algorithm, in this token, it's way different, right? With my algorithm, it's different in this token. So it's interesting view of how these various ways of speeding up the whole process affect the tokens that are there. So you can see that some of the tokens with quantization, their quantization has problems. Some of the tokens, my algorithm has problems, it's not one-to-one, right? So it's interesting, again, point of view for the research. And the one last thing, and I'm surprised that no one actually did that for this view for regular quantization. Let me zoom in slightly. So what I did is, and I don't think anyone created this heat map. So when you have a metric of how far away is the model, what you can do is you can make a heat map. So we have an article here, so like some random article about birds, right? And on top of it is where my effort, with my algorithm, when you get lower in effort, where the words start to diverge, right? So you can see here, if it's white, then it's like the same, right? The algorithm would make the same prediction. If it's red, there is a huge divergence. It's an interesting way of looking at things, and I don't think people even do that with quantization. So I think it might be interesting if we start to look at models from this perspective, and then say, what's here, right? Like,
can it goes back to your measure of difference on the being very mathematical in the first place, and then just visualizing it this way is useful.
So there are a few things that are interesting from the perspective of research, right? And
there might be one takeaway for a lot of people who are building apps who are doing evals for just kind of regular inference applications, right, is to build a heat map for your evals like this. You could do that for another domain. It doesn't have to be for this problem. That's a great idea. So
more or less that's it. Like I said, sadly, quantization, and it's one of the things about scientific, honestly, you have to say, if something is better, then you have to say that it's better, right? So quantization is better, or at least it's, perhaps I could get this algorithm to be as good. But it opens up interesting fields of research that I think aren't that much explored. And again, what models do, all in all, is still an open question in many cases, right? And any new lens that we have is maybe interesting.
Well, okay, before we wrap, I want to touch on you and the community a little bit more. Again, Artur said, like, the OG tinkerer is Thomas, and, you've clearly had a long career here and done lots of interesting things. We didn't touch on many of them, actually, but I do want to touch on a couple of them, and also just how small the community is, too. I think when I got here, you said, I said I was just with the 11 Labs founders in London, and they're from Poland, of course. And you pointed out the windows to their offices right there.
I think so. They told me that it's in Hotel Europa. Over there.
So that's a small world. I love it when you come to a place and meet people, and you feel small all of a sudden, and that's great. Speaking of that, like meeting people, getting together, you started a kind of incubator garage or hacker house kind of a concept here.
That was fun. We rented after so many years in software, one day you wake up and you're tempted to do something big and something loud and weld something or do things like this. And really,
the free space Warsaw.
Free space, exactly. So me and my friend were looking for a year for a place that would be close to the city center where we could just do cool stuff, build cool stuff, and an idea for a while was to have an accelerator.
Do you have photos of it?
Actually, I have it.
Yeah, cool.
I don't have too many photos, and of course, photos don't really do it justice. But
but it gives the people.
That's my friend Norbert. So it used to be actually a car chop shop. So we found a lot of license plates of cars that were that ended their life here, right? So we cleaned it up, and we have like this a small part of this whole place, and we have a place where we can do various cool things. One of the ideas was that I wanted to venture builder related to climate tech here in Poland, but one thing is climate tech is not very big in Poland, sadly. Second thing is AI is way more interesting right now, so I decided to focus full time on AI.
And you were at the very first AI Tinkers meetup.
Just one more thing. Because of my background in startups, I love having startups there, and right now the place serves as a hub, as a meeting place for a lot of startups, and we're doing meetups there, and
cool.
It's a nice atmosphere. And what people say is, Google campus is nice, like it's nice to have these offices and everything, right? But when it comes to this garage atmosphere that at least people hear from,
it's more appropriate for
so this is the place where you can drill a hole in the wall
and stuff, build stuff,
exactly.
Share.
So I'm not objective, but people tend to say that it's super inspirational to be there.
That's really cool. That's nice. And you have the robot.
The robot is there, but that's thing for another story.
So what was the story there? You just decided like you need to go buy a Unitree robot and start hacking it?
The thing is, my story, I think what I'm good at is trying to hit technologies trends way before they happen. With AI, I feel very weird because I'm kind of not late to the game, but just I arrived with everyone else. Of course, I was interested in AI during my computer science and
well, we didn't talk about it, but you did the Bitcoin.
But I left the crypto community.
You weren't a crypto bro, that's for sure.
I wasn't a crypto bro. I was the tech crypto person, and the technology there is quite nice. I built some cool stuff and some amazing people that I've met there. But with AI, I built chatbots. I tried to set up a chatbot startup in 2007 actually, so that's been way before its time. And again, when there is a new technology, I try to figure out what's it about. And the robot that you see in the background, it's a Unitree robot, and they're super cheap right now, 2,000 euros. That is extremely cheap.
Wow.
And it's nice to see what they're about, how far it is.
How hackable is it? Like, what can you do?
That's the guys that were on the hackathon that I borrowed them, but I think it is hackable. I would love for them to. They have this other version that is educational, that is that has an open SDK and has some accessories, but that version is way better. I would love them to give access to that version. But by itself, this robot it's a nice piece of technology. So if you can afford it, I would say go for it, especially before the tariffs hit.
Cool.
Very much. But speaking of AI tinkerers, if I can add one more thing, and a word of praise towards AI tinkerers. We have a lot of communities here, AI communities, whatnot, startup communities. And also, speaking of this algorithm, I spoke about it with many people super technical. AI Tinkerers was the only place where I gave a 5-minute presentation, and the questions I got from the room were questions that showed such a deep understanding that I didn't have these questions after an hour of talk with a fellow computer scientist.
Cool.
And I was so amazed by the quality of the people and the discussion afterwards. That was something amazing, and that was we have a lot of cool technical people here in Warsaw, and you managed to grab all of them and invite them to AI Tinkerers. So I respect that.
Thanks. Be sure if you're on the road and you're in another city, stop by one of the chapters. We had, it's funny at the hackathon we just had here in Warsaw. I went through the data, and there were people from AI Tinkerers chapters around the world. Yeah, we had somebody from Kuala Lumpur, Medellin, Colombia, of course, all over Europe. So that was exciting to see.
That is also one thing that I was really missing, this community aspect of AI. And again, the cool thing about the blockchain community is that it's so well connected, and it has hackathons every single week happening somewhere else, right? And people meet in person. And of course, it's easier because the budgets are better and whatnot over there than with some AI projects.
They have the money, but not the applications.
So the applications, real world applications, are missing a little bit.
The applications.
But now the community, when I left the community, I was really missing that human aspect. And of course, there are Slacks, there are Discords, but AI Tinkerers is this one missing community, that thing that I was really missing from the AI community. So I'm very grateful for doing the whole thing.
Yeah, Arthur and Andres and everyone here has done a great job, and it's a very fun thing.
Yeah, definitely.
Thank you. Well, where can people find out about more of your work? We shared the GitHub URLs or any other thing you'd like
GitHub URL is one thing. Right now I'm on a sabbatical, so I do totally different.
What is next?
Right now for me, dancing, right? I'm focusing full time, but I think I will, it's hard to be on a sabbatical during such exciting times, right? Sure. So I'm already brainstorming some of the ideas.
Nice.
I don't know personally, perhaps I will go deeper into research, or I will try to do a new project, startup. We'll see. Awesome. But I would say if you want to follow me, go onto Twitter. Cool. Kolinko is my handle there. I don't tweet that much, but when I start a new thing, I will. You will. There will be tweets over there.
We'll follow along and we'll check in on you. This is great to meet.
Cool.
Thank you so much for your time.
Thanks for the space.
Thank you.